All right, we're going to run through an example of translating a proposition, a verbal proposition expressed verbally, into a symbolic statement, and then translating that symbolic statement into a circuit diagram. So first, let's look at the proposition. If I go to class or to work, then I will not go running. Right, so in order for us to express this symbolically, we first need to establish what are the individual propositional variables involved in this statement. Well, one is I go to class, right? Another one would be I go to work, okay? And then the third one would be I go running. And we do have some operations in here. I prefer to express all of my individual propositional variables in a sort of affirmative way with a positive thing, so as to avoid any double negatives that I might get otherwise. So I'm not going to express one of my variables as I will not go running. I'm going to express it as I go running, and then I can describe the not with an operation, with a negation operation. So let's write down our variables. I'm going to name them P, Q, and R. So we have P is going to represent the statement, I go running. Oh, no, sorry. Let me get that right. It's going to be I go to class. Here we go. Q will represent the next one, which is I go to work. Okay. And then R is going to be the next one, which is I go running. Okay. And now now I'm going to read this with all of the operations that are expressed here. We have an if, we have an if-then overall. We also have an or, and then we have a not. Okay, and it's sort of implied that this here is like in parentheses. I go to class or to work, right? So that all of that is part of my hypothesis over here. Hypothesis for the that's the hypothesis for the conditional statement, and then this over here, I will not go running, that is the conclusion of the conditional statement. So, if then, let's start by writing down the hypothesis. It's going to be I go to class or to work. So that's just P or Q. So I'll write P or Q. That I'm going to put it in parentheses. That's the hypothesis. And so now I'll put implies, that's the if then. Now I need to write down the conclusion. The conclusion is I will not go running. That's just the negation of R, not R. So we have P or Q implies not R. And that is the symbolic representation. So let's label this as number 2 here. That's the symbolic representation of, I guess I can put it over here, of number 1, of the verbal statement. So now the question is, how do we make a circuit diagram for this statement? Because we only have gates for not and an or. So this is where in the last section I introduced, let me get it out here. I introduced this propositional equivalence. P implies Q is equivalent to not P or Q. So we can apply that here. Our hypothesis is P or Q. So P or Q implies not R is actually going to be equivalent to the negation of the hypothesis, P or Q, or the conclusion, which is R. So we have not P or Q, or not R. There we go. So just using that one equivalence, identity essentially, we've been able to write it in a way that doesn't use the arrow and instead just uses ors and negations. This doesn't even involve any ands. So now we can take that and translate that directly into a circuit diagram. So this is going to be representation number 3. We have our three input signals, P, Q, and R. So we write those on the left or wherever. And those are like 3 wires. And so now what we want to do is combine them according to this. And we have to pay attention to the order of operations. Sometimes, by the way, you need to split. If you ever need to split into 2 signals, you can just split your wire into 2 wires and the signal gets sent in both directions. That's fine. You can do that if you need to. And we'll look at some examples of that in a few minutes. But for this one, all we need to do is take P and Q and combine them with the OR operation. So I'm going to go ahead and stick the P and the Q through a OR gate, like that. So now what we have here is P or Q. That's the truth value of that compound portion, the portion of that like chunk of the compound proposition. So now the next thing we would need to do, according to the order of operations, is negate that. So now I'm going to take that signal and send it through an inverter, a negation, a NOT gate. So now what's coming out the other end here is the negation of that. So now this signal, it carries the entire first part of this disjunction. Now we're going to have to do an OR, but the other part of the disjunction is not OR. So down here, I've got to send R through a negator, again, like that. Here we go. And now I've got these two wires, and these now represent this entire chunk and this entire chunk. So I just need to combine them with an OR gate, like that. And there we go. There is my circuit diagram that is going to take the input values of P, Q, and R, right? The truth values of these three variables, and then it's going to compute the truth value of this statement. If I go to class or to work, then I will not go running. Okay, that's the whole process. Now I'll leave you with one question. This has 1, 2, 3, 4 logic gates in total. Can it be simplified? Is there anything we could do to this that might simplify it by decreasing the number of logic gates that are involved in this circuit? Could we take this circuit and make it smaller? I'll leave you to think about that, and we can discuss that in class.